Hi, this is John, and this is lecture 4 for week 3 of CS 1030. So today we're going to talk about lists, but before we get into that, I just want to give some general advice about doing assignments for this course. So as you've probably noticed by now, and if you haven't, you'll likely run into this sooner or later, it can be hard to know what to do when you're writing a computer program. It can be hard to take some sort of a conceptual solution, which you probably have some pretty good understanding of how to solve the problem we've given you, and then turn that into actual code. It's just hard. It's easy to get roadblocked here. It can be frustrating. And what I'd like to do is just try to give you some general advice for how to do this, and hopefully it'll be helpful. So one thing you really should be able to do is describe the solution in English before you start writing the program. So if you could explain it to a friend, a roommate, somebody you know, somebody else in the class, that's really helpful. And it's helpful to do even before you start writing pseudocode. So then, of course, once you can explain it in English to a friend, then you'd also want to write pseudocode. And you should do this before even sitting down to write any Scratch code or code in any other language. And of course, you don't have to do this, right? If you can sit down and write the code, if you can write the Scratch immediately, then that's fine. You should just do that. But if you're having trouble, then go through these other steps. Describe the process in English and sort of bounce it off a friend and try to get feedback and see if that works. And then also write pseudocode. So the next piece of advice is always, always, always build on something that works. So it's almost impossible to solve a complete computer program, sort of to write it from scratch and make it work. And none of us can do this. So what we do is we build something much simpler than what we're trying to build, and we make sure it works. We test it, we prod it, we sort of play with it, and then we add more features. And this is the way essentially all programming works for all of us all throughout our lives. And you should just basically get used to working that way. Because even if with the kind of easy assignments we're giving you here, you can sit down and do the whole thing at once, that's not going to last as you get to more challenging problems in other courses. So another thing you should do is spend a lot of time testing your code. Just see what it does in various circumstances and make sure you can explain what you see. If the code does something that you didn't expect, then what that means is that this is your computer program telling you that you didn't understand something about the program, that what you wrote down isn't somehow what you intended to write down. And you need to understand that and try to fix it. Another good thing to do is just explicitly try to break your program. Try to make it go wrong. Try to walk off the edge of the screen in a computer game. Try to make the score negative. Try to do things that are going to make it break. And if you can break your own code, then you know what to fix now. There's a hole in the logic of some sort. If you break somebody else's code, it's just fun. It just means that you're good at breaking things. And finally, if your code gets to a point where you really just are frustrated with it and you can't understand what's going on and it's just a mess, it's often best just to completely start over. This is an option we typically don't have in industry, in real life, but the problems you're solving for us in CS 1030 are easy enough that you should almost always be able to just delete everything and start over, and then try to avoid getting into whatever problem tangled you up and got it so you couldn't understand your program in the first place. Anyway, so this is going to be a process for you. It's been a many decade-long process for me trying to learn how to follow this kind of advice, and it's just going to take time. And that's sort of unfortunately or fortunately, I don't know really if it's good or bad, unfortunately, but that's how things work here. Okay, so let's get on to the main content of the lecture. So in a previous lecture, we talked about building a to-do list, and if you remember, the implementation strategy for the to-do list was to create a state variable for every item that might or might not be on the to-do list. So remember, one of them was something like do our homework or whatever. So in this implementation strategy for a to-do list, we set that state variable corresponding to do our homework or whatever to 0 to indicate that it's not currently an item that's on our to-do list, and set it to 1 to indicate that it is currently on the to-do list. And then once we do the item that's on the list, we can set the value of that variable from 1 to 0, and that removes it from our list. So this works. It's perfectly acceptable at some level, but I hope it's kind of obvious that this is a poor way to build a list. It's not really going to scale up to 1,000 or 1,000,000 items that could be on a list. So let's look at how to do better. So almost all programming languages, and Scratch is included, have a built-in list construct of some sort. So let's look at Scratch's list. So I've shown on the right part of the slide here what Scratch shows you for a list. So let's look at the elements of this. So the name of this list is grades. And so when you create a list in Scratch, there's a button for this along the left side of the sort of main Scratch screen. You give every list that you create a name. This one's called grades. And grades has 4 items. And it's really important that items in a list are ordered. So any item in a list is in a particular position at any given time. And if you have two different lists that contain the same items, but they're in a different order, those lists aren't the same as each other. So in contrast, if you remember from math in high school, if we have something that's called a set contains some items, but the order of the items in a set doesn't matter. So lists aren't like that. So this list has length 4. That means there's 4 things in the list. And the 4 things are 92, 67, 96, and 85. So these are just integers as far as Scratch is concerned. But we can sort of tell by looking at the name of the list and by the magnitude of the numbers that these are probably percentages that we've gotten on some sort of assignments in a class. And so one of the really nice things about lists is that they expand as needed. So you can add or remove things. So this list contains 4 elements, but we could add a whole bunch more things, and then the list would eventually contain 40 elements or 4,000 elements. And again, one of the important things about a list is the order matters. So the grade 92 is at position 1 in the list. It's the first item in the list, and that sort of matters for the list. Okay, so lists are incredibly important in programming. Again, and every real programming language, or almost every real programming language, supports them, but they're under different names. So lists, they can be called lists, queues, arrays, vectors, tuples. There's a lot of different terminology for this. And one of the things you're going to need to learn as an aspiring computer scientist is that we do this a lot. We take the same concept and we have a lot of different words for it. And these words sort of differ depending on our background. So if you ask a Java programmer what they use for a list, they may have a completely different word for it, or a programmer in some other, JavaScript or whatever programming language, they're not going to talk about things quite the same way that we're teaching you to talk about them here. And you just need to sort of learn to roll with this. It's just a kind of a fact of computer programming culture that a lot of terms exist that often refer to the same thing. And you just need to take some time to get used to this. So it's not great. It's not a great feature of the field of computer science, but it's something we have to get used to. So if your computer programming language supports a list, which again, it almost certainly does, we can ask some questions about it. Is the list fixed sized, or is it resizable? So once we create the list, can we add and remove things, or is the list sort of stuck in its current state? Another question is, can this particular list contain different kinds of things, or is a list only contain elements which are of the same type? So the list example that we looked at earlier with the grades contained all of the same kind of thing. Every element of that list was a number. And so sometimes that's what we want. And other times what we want is a list that contained different things. So it could contain 67 in entry 1 of the list, and it could contain John in entry 2 of the list. So those would be 2 different things because 67 is a number and John is a string. So some lists work one way and some lists work the other way, and you should just be prepared to accept that these different things exist. A really important question is what operations are supported on the list. Can we add things only at the end, or can we add them in the middle or in the beginning? Is there an operation for alphabetizing the list, for example? And then finally, and this is a little bit more subtle than the previous bullets on this list, how much memory does the list, how much memory does the list use? Some lists are very efficient and you could store millions or billions of things, and other lists are represented in a way that uses memory inefficiently. And in this kind of list, you may only be able to store a few thousand or a few tens of thousands of things before your computer sort of grinds to a halt because you've used all of its memory. And this kind of memory issue is not something we're going to spend a ton of time talking about in 1030, but it is important as we become more sophisticated at programming. And so the answers to these questions will determine whether the list abstraction provided by the programming language is useful to solve a problem that you have. So you have some sort of list of, I shouldn't say this, you have some sort of requirements for the list. It's in things you need to do with it in order to use it in your program. Then the list provided by the programming language is going to have some features that it offers, like the things mentioned on this slide. And if those match up, the list will be good for solving your particular problem. If they don't match up, then you may need to find some other different list or build a list yourself or something. So let's talk about manipulating lists. So lists in Scratch can be modified dynamically, so you can change them once they're created. And one of the things you can do is insert a value to a list at a particular location, and you can also delete the item in a list at a particular location. And we specify the item to be deleted not by the value, but rather by the position. So if I want to remove the score of 92 from the list of grades on the right-hand part of the slide here, I don't tell Scratch to delete 92. I tell Scratch to delete the item at position 1 of the list, and that deletes 92 from the list. So this is sort of important, and the thing that's going on here is that we've sort of used this index or the position in the list as kind of a level of abstraction. So instead of talking about the actual data, we're talking about the position. And so one question we might ask is, why is that a good idea? Why do we want to specify it that way? And one of the answers is, for example, if the list contained 92 7 times, we wouldn't know which one to delete if we just said delete 92. Scratch wouldn't know which one to delete. So if we specify the position, then it'll of course just delete whatever's there. So there's sort of pros and cons of this kind of a scheme, but that's how it works here, and this is how it usually works in most programming languages. And I just want to address the fact here that this can be confusing. And the confusing thing comes from the fact that the position in the list is an integer, that is to say just a number, and this list happens to contain values that are also integers. And I can almost guarantee you that at some point in your career here in 1030, that is to say in the near future, you will get confused between whether you're talking about the thing in the list or the position of the thing in the list. And this will cause your programs to mess up if you don't get this completely straight in your own mind and in your program. And I'm just warning you to try to keep this straight, that there is a difference between the position of the thing in the list and the value of the thing in the list. And you need to kind of, you need to be clear about this again in your mind and in your program, or else it's going to be hard to write things that actually work. So index numbers, that is to say, integers that identify positions in lists are an abstraction. They allow us to sort of step away from the contents of the list and only refer to the location. And this is an example of an incredibly important concept in computer science called indirection, where we don't refer to what's there, we just refer to where something is. And you can see a lot of examples of this kind of thing in real life. So for example, if I want to describe to you how to get to my house, I don't tell you about the shape of the house. I don't tell you what's in it. I don't tell you what it looks like. I just tell you the address. So that's an abstraction of my house that allows you to actually find it, and it's more useful for that particular purpose. So in general, this is sort of, like I say, a key concept. It's going to come up a lot, and we just want to sort of start introducing it to you here. So let's next ask how we can look at each item in a list. So how can we display every item in a list? And it turns out that Scratch does have a single command that can do this. We can say items to say everything in a list, but this isn't very flexible. It doesn't allow us to actually work with the items in a list. For example, if we wanted to go through all the items in a list and filter out the ones that are too high, this particular code here wouldn't let us do it. So the question is, how can we write code that processes the elements in a list in order to, for example, do something with them? So here's some code that does that. So when we click the green flag, this Scratch code runs. So again, as always in Scratch, the code here is attached to some sort of a sprite. So what we're going to do is set a new variable called index to 1. And now we're going to have a repeat construct, a repeat loop, which repeats the same number of times as the list has items. So Scratch has a built-in way to get the length of a list. It's just this length block here. We tell it which list we want the length of, and now this whole loop is going to execute as many times as there are things in the list. So this is a very good and natural way to look at all the items in the list. So now the action for this loop is to say the item of the items list at the current index for 2 seconds. So hopefully all those pieces sort of make sense to you at this point in the course. The item construct looks up what's in a list at a particular place, and index is what that place is. Index is the variable that we set to 1 at the beginning. So initially, on the first time through the loop, we're going to say the first thing in the loop. Then we're going to change index by 1. That is to say, we're going to add 1 to index, and we're going to keep doing it. And so what hopefully is clear to you here is that this ends up saying, for 2 seconds, everything that's in the list called items. And this is a real sort of, typical example of a repetition construct where we have a setup, again, we have the loop itself. Inside the loop, we're going to do something and then we're going to change a variable, change a state variable in order to update the state of the loop so we can do the next thing the next time through the loop. And so something I would suggest not doing in this kind of a loop is modifying the list while you're inside the loop, because we have to start asking awkward questions like, does the length of the list look at it at the beginning, or does it update the length as we sort of start changing the loop? And so let's just not go into that right now. So again, it's best if in this kind of loop you don't alter the loop as you're changing it, because we can get into sort of problems with our logic fairly quickly in that case. So before finishing this piece of the lecture, let's look at a different way to look through a loop. So we can, again, repeat for the length of the items. Then every time through the loop, say the contents of the list that's at the beginning of the list items for 2 seconds, and we can just delete that item. And so if we do that, what's going to happen is we delete the item at the beginning of the list, and then the next time we execute the body of the loop, there's a new item at the beginning of the list. We say that, and then we delete that one. And so we can ask ourselves if this is better or worse. So it's almost certainly worse, because first of all, it does the confusing thing that I was talking about on the previous slide. It modifies a list as we're iterating through it. And secondly, what if we wanted to use this list again later? What if we wanted to use this later? Well, the problem is we've just destroyed the entire list when this repetition construct finishes. So this probably isn't the way to do it. I'm just showing you because there's often a lot of different ways to do things. There's often trade-offs between them. This is most likely not the one you want. Thank you.